well, so I get a full recording, but okay. And how would we represent those electrons? What little symbol do we use? We use a little arrow. So we might draw an arrow like this. And then what would the other arrow have to do? It would have to point downwards, okay? Now you might also see this drawn like this with little half arrows. That's another way of doing it. So you'll see full arrows, you'll see half arrows, whatever, okay? And if you're interested in what the up and down means, it has to do with the spin of the electron. Okay, so the up means it's spinning one way and the down means it's spinning the other way. Yeah, I think so. And so, but if one's spinning, then electromagnetic stuff happens because moving charges do things, which I don't understand, but they do. Yes? We call those two spins spin up and spin down. I don't know why. So s orbitals are really nice. S stands for sphere. That's lovely. They have only one.
So wait, so they get larger?
At every energy level, the s orbital is further from the nucleus. So the one at energy level 1 contains one s orbital. Yeah? Energy level 2 contains an s orbital further from the nucleus. Yes. Now, p orbitals are shaped like peanuts. Now, if you've never seen a peanut in a shell, you're probably like, that doesn't look anything like a peanut. But let's take a look at a peanut in a shell. Right? Peanut in a shell. Do you see how they kind of got like that little indent in the middle? Yeah? So that's what we kind of think of them as being like. We've got the one little peanut over here and the other little peanut over here and then the indent in the middle. Okay? So they're shaped like peanuts. How many p orbitals are there in a p subshell? There are 3 p orbitals in a p subshell. So if we were to have, let's say, energy level 2, n equals 2, we would have 3 orbitals that all have equal energy. Yes? This is a 2p facing in the x direction. It goes along the x-axis. 2px. We have a second one that goes in a different direction. It's the 2py. It goes along the y-axis. So those are perpendicular to one another. Okay, one's going this way, one's going that way. I'm going to stand up on a little step stool. If I can find my step. There's my step stool. So we have a px, we have a py. Everyone show me px and py. Px and py. Which direction is pz going to go? So they are all perpendicular to each other. They're all at what degrees? 90 degrees. So the 3p orbitals, they're all perpendicular to each other. And one thing you're going to notice about these, what do you see at the center there? At the nucleus, what happens? They go... That's called a node. A node is where there are no electrons. Isn't that nice? Node. There's no probability of finding an electron there.
Like the middle?
Yeah, right in the middle.
No, like
There's no probability of finding an electron at the nucleus.
that's basically the pink ones. It's like highlight where the electron.
Yeah. So do you remember that video and we took like a time-lapse photograph, right? And it looked like, you know, we filled in this and we filled in this, and like there was less probability as we got towards the outside, and the greatest density was towards the center of each little blob. Okay. Yeah, kind of like that. I didn't do a very great job. So the node in the middle is where the nucleus is, and there is no probability of finding an electron there. Now, one thing to remember is that even though the p orbital has two lobes, this together is a single orbital. Okay, these two together is a single orbital. This is not an orbital. This is the orbital. How many electrons can be contained in each orbital? 2, just like every other orbital. Every orbital in the universe can contain a maximum of 2 electrons. So we have a 2px, we have a 2py, and we have a 2pz. Each can contain maximum of 2 electrons. And all 3 of these are all at the same energy. Okay, they're all at the same potential energy. Yes? One side to another? Okay, that's a really good question. Like, is it just teleporting, right? So this is where that particle wave duality comes in. So the electron, if I take a photograph of it, here it is. Okay, because I'm interacting with it when I make a measurement of it, and it's like, oh, there I am. And then I stop interacting with that electron, okay? And when you leave an electron on its own, it disintegrates into a wave function, which is a probability field. So it is no longer a point. It's no longer a little ball of matter. It is now just a wave, which takes on, and don't ask me how a wave is a blobby shape. That requires way more math than this poor little brain can handle. Okay, so much math, right? But math explains it. This is a wave. It's called a wave function. It's essentially a probability field of where you will find that 1 or 2 electrons that are living in that orbital. Yeah? Yes.
Wait, I said it right.
What? Sorry? You can think of it like the electron is constantly moving within there, or you can just think, oh, it is a wave and it is this shape and it is a probability field until I look at it. And when I look at it, all of a sudden, there it is. How does it go between? Because it is the shape. It's the entire shape, right? So when it collapses from the 2 balloons into the little particle, so it's like, I'm 2 balloons, la, 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 right? It's a wave. It's not a particle. Okay, so instead of being a little dot, it's just a blobby shape. Okay? And then it collapses. It can collapse over here, or it can collapse over here. It cannot collapse right in the middle. And if this is making you super happy, then I invite you to go get your PhD in particle physics, okay? Because like, if you're like, wow, that totally made sense to me and I can totally understand that, probably particle physics is going to be your jam. It's not my jam. So if you're like, this makes no sense to me whatsoever, that's okay. Einstein didn't like it either, and he was a really smart guy. So there we are. Okay? So we have, and blobby shape, it collapses. Blobby shape, we look at it, it collapses. And as you do that over time, you will end up with that electron showing up in each area of the blobby shape, never at the node. Yes? Are you going to have to explain this for the AP exam? Absolutely not. You just need to know that the shape of a p orbital is like this. And then it goes 1, 2, 3. Okay? Yes? Shh. What? Yes. The electron behaves as a wave. But if it is interfered with, so if you're measuring it in some way, if you're throwing a photon at it, if you're doing anything with it, then it becomes a particle. Then it acts like a particle. But if you're not doing something with it, it acts like a wave. Yes?
So the reason why there's like getting going.
Yes.
How are they different?
Pardon me?
How are they different?
How are they different? Their orientation in space is different. So one goes up, one goes sideways, and one goes forward and backwards. But their energies are the same. Okay? So
it's like a forward or backward.
Oh, it doesn't matter. I mean, you could have one of the p orbitals oriented in space like this. Right? That just means that the second one has to be like this and the third one has to be like that.
Why is there all right? Because there's
right? Yeah. And so if you have one electron in that subshell, we got Ruslana and Dylan is not there today. Thank you.
So basically, it's like the 2 different orbitals on the base.
Pardon me?
Started 3 different orbitals.
Those are the 3 different orbitals in the p sublevel. Yes. Yes, every orbital can contain 2 electrons. That doesn't mean it does. I mean, if you only have 3 electrons to spread out, then it's going to be 1, 2, 3. If you only have 2 electrons, you're only going to have 1, 2. Yeah, so let's say, Sylvia, could you shut the door for us, please? There's a lot of traffic out in the hallway. Thank you so much. Yeah, let's say we had 2 electrons in our py orbital over here, and we did something with it to measure them. One of them could appear here and one could appear here. Or you could have one there and the other in the other side. So don't think that one of the electrons lives in one lobe and the other lives in the other lobe. They both live in both lobes. Yeah? Okay. So, like I said, don't get too stressed about it. All you need to know is at the energy level 2, you have a 2px, a 2py, and a 2pz, and these all have the same potential energy. Because if you look at them, the electrons within them are all at the same distance from the nucleus because they are all identical. Yes?
Does that mean the 2s orbitals have less potential energy?
Yes, the 2s orbitals have less potential energy than the 2p orbitals. Not by a lot, but by a little bit, because they're a little bit lower, so they are at a lower potential energy. Okay? Now, D's. These are going to make you so happy because you remember how I said all the P's are identical, which is why they all have the same energy. Well, the D's are all identical except for the word D, Z2 squared. But in terms of energy, apparently it is identical to the other ones. So we have, I call the D ones the daisies. Okay? D for daisy. Sometimes people will call it the double dumbbell donut because you have a dumbbell here, right? You guys know what a dumbbell is, like one of those things. You have a dumbbell here. So double dumbbell, and then this last one here has a donut.
What?
I know. I'm like, I don't know. Waves, they're weird, right? So those are the 5 shapes of the D orbitals. What happened here? Come on. Oh, hang on. Yes.
The orbitals, the square is just there to show that.
Yeah, the square is just showing the plane. Okay, so it's showing you the XY plane, the YZ plane. So we have YZ, we have XZ, we have XY. You don't need to be able to name those. Okay, you just need to know that there are 5 d orbitals and they all have the same energy. Yes, and they don't show up until energy level 3. And then finally, we have our F orbitals. And the F orbitals are fancy. Okay? So we have some like little donuts and things, and then we have like 8-lobed whatsy-woos, right? We still have nodes, right? We got a node at the center. We got a node. Do you need to know any of these shapes? No. Okay. Sometimes people call these flower, F for flower. None of them stand for any of that. I think S is sphere, P is something, D stands for diffuse, I think. But like those names mean nothing to me, so like I just ignore them, okay? And then we have a summary of all the shapes so that you can see them, okay, all on one page, right? We have our, what is this first one? What is the sphere? S, and then we have P, and then we have D, and then we have F. And if you have trouble remembering the order, you can remember that speed is fast. Okay, so if you have any trouble remembering that SPDF, speed is fast. So S is at n greater than or equal to 1. P's are at n greater than or equal to 2. D's are at n greater than or equal to 3. And F's are at n greater than or equal to 4. So we don't end up with F's orbitals until shell number 4.
It doesn't change.
So here is energy level 1. Here's energy level 1. It's just got the 1s orbital. Here's energy level 2. We have a 1s orbital and we have 3 p orbitals. I haven't bothered putting them at different energy levels because it got just in terms of fitting everything on the page, it wasn't going to work. Okay, but at energy level 2, we have a single s orbital and so we have a 2s and we have a 2p subshell. Okay, and then at n equals 3, we have sometimes you'll see p orbitals, rather than being quite so balloon-like, they'll just kind of draw them as blobs. Yes? So at n equals 3, we have the 3s, we have the 3p, and then we have the 3d. Okay, so your homework is going to include 9.3c. I'll figure out what else and I'll pop it up on Teams. That's not going to be it because you've got a whole weekend and I want you to make sure that you are good with everything. Okay.